Hello everybody, today we're going to talk about Kirchhoff's laws, which are KCL and KVL. So far we have only learned one law, which is Ohm's law, which is not sufficient by itself in order to analyze all the circuits we have. The German physicist Gustav Robert Kirchhoff actually introduced a couple of laws that are going to help us really good, and actually KCL and KVL are also foundations of some circuit methods. So thanks to these KCL and KVL, which are Kirchhoff's law, we are now able to analyze lots of circuits. So this lecture is going to be really important because I told you that previously. Ohm's law is the most important law in electrical engineering. That is still correct, but Kirchhoff's current law and also voltage law are really important throughout this course, so you should listen really carefully. So basically, Kirchhoff's laws, there are two laws. The first one is KCL, and the second one is KVL, and they are different in some ways. First of all, KCL is standing for Kirchhoff's current law, as you can understand, and KVL is Kirchhoff's voltage law. So KCL, which is current law, is depending on, and it would be better if I just say, it is based on conservation of charge. KVL, on the other hand, is based on conservation of energy. First of all, we're going to start with KCL, which is based on conservation of charge. Let me put a huge title in here, KCL, conservation of charge. Basically, KCL states the fact that the algebraic sum of the currents entering a node, and by the way, we have learned what a node is in the previous lecture, must be zero. I'm going to put the definition in here, and we are also going to talk about the math-wise relationship of this law. We can actually represent this situation mathematically by using a summation sign. So we're going to put it this way. N is starting from 1, and N in here, the capital N, is representing the number of nodes we have in the circuit. IN, the currents entering to that node, must be equal to 0. And this is the mathematical representation. But when we think about it in this way, we can simply say that we need some sort of polarity in here. Not polarity, but convention would be a better word. You know why? Because we're talking about a node, and we are also saying that the algebraic sum of the currents entering that node must sum up to 0, meaning that when you think about it, some of the currents enter the node and some of the currents leave the node. So we must have a convention. And throughout this course, the convention that I'm going to use is that the entering currents will be treated as negative and the leaving currents will be treated as positive. This is really important. This convention is really important. You're going to see the importance in a couple of minutes ago. You could do the vice versa. I mean, you could just take leaving currents as negative and entering currents as positive. But the problem is you need to be really careful. And also, since we're talking about a convention, I mean, it doesn't matter which way you choose to go. This is basically a reference point. However, the problem is a lot of people are actually taking this convention as entering currents are negative and leaving currents are positive. So if you want to actually get in worldwide, if you don't want to have any problems with the convention, because lots of people are using the convention that I'm going to use, it would be better if you just move on with this one. You are going to treat entering currents as negative and leaving currents as positive, and I will show you what is that supposed to mean in a minute. But just in case, if you want to find out, if you are interested in the proof of KCL, let me show you. Actually, I don't have any space. Oh, here I have any space. Here I have some space, and let's prove KCL. How are we going to do that? First of all, the idea is that the sum of the currents, the algebraic sum of the currents entering a node must be 0. So what I'm going to say is IT of t, which is going to sum up to 0, must be equal to I1 of t. Let's say I have current 1, current 2, and let's say maybe 3. and let's say blah blah blah, it goes on like until in of t. So when you think about it, if I just integrate both sides, I mean left side and right side, what would I have is going to be something like this. Qt of t is going to be equal to q1 of t plus q2 of t and q3 of t, and it goes on like that, qn of t. So this is possible. You know why? Because let me actually go a little bit above. We know the fact that, I mean, from the previous lectures, we have learned that the current and charge relationship is really clear, which is that I of t is equal to dq over dt. When you integrate both sides, you're going to have the integral of current on the left side, and on the right side, you're going to have the charge. So we are doing exactly the same thing actually. When we take the integral on above equation, we get the below equation. So this equation is really important because now we can easily see that the charge is conserved. You know why? Because the net charge sums up to 0 because you cannot create charge and you cannot ignore the charge. Basically, the node is storing no charge, so that means entering charge must be equal to leaving charge. So this is the proof, because we're going to say if qt of t is 0, and by the way it is because conservation of charge is a law, you know. So if qt of t is 0, then it of t must be 0 too, and this is the proof of KCL. Now what we're going to do is we're going to check out the example in here because we're going to learn something from there. So basically we said that we're going to take entering currents as negative and leaving currents as positive. So when you check out here in the middle, we have a node. So I1 is entering the node. So what I'm going to say is minus I1. And also I2 is leaving the node. So that's going to be positive. This is what I mean by convention. And I3 is entering the node. So that's going to be negative. And I4 is also entering the node. That's also going to be negative. And in the end, I5 is leaving the node. So that's going to be positive. And all these must be equal to 0. So when we do a little bit of an arrangement in here, we can take I1, I3, and I4 on the other side of the equation. So on the left side, I2 plus I5 must be equal to I1 plus I3 plus I4. So this equation is actually giving us another alternative way to define KCL, which is that instead of saying the algebraic sum of currents entering or leaving a node must sum up to 0, we can also say the entering currents must be equal to the leaving currents. This is another alternative way to define KCL. This is how we are going to do it. I mean, there are two ways. You can also say, I mean, the entering and leaving currents must sum up to 0, but this is another way. The entering currents must be equal to the leaving currents so that actually KCL holds. So a simple application of KCL, which is given in the figure right in here, is combining current sources in parallel. As you can see, we have 3 sources, and I know we have not talked about series and parallel connection, but these current sources are connected in parallel. The combined current in here is going to be the algebraic sum of the current supplied by the individual sources. For instance, here we have 3 individual sources, I1, I2, and I3. And on the right side, we have only one source, which is simply a combination of the other 3 individual ones. So let's see how is that going to work out. So here, as we previously spoken about it, here we have only one node. We have 3 points, and they actually form one node, and let's say that node is A. So according to KCL, we know for a fact the currents entering a node must be equal to the currents leaving the node. So basically, I can simply say that I1 is entering, as you can see in this way, and also I3 is entering. Let me put them on the left side. They must be equal to I2. Or in another way, you can do this mathematics by saying entering currents are negative and leaving currents are positive. So minus I1 plus I2 minus I3 must sum up to a 0. So in this manner, actually, when you check out by this exact equation, we find the one single current source that could actually replace these 3 individual sources in this manner, and we are able to do that by using KCL. And now it is time to talk about KVL. Let's do it in here. KVL is no different than KCL except for a couple of points. In here, we define KCL as the algebraic sum of the currents must sum up to 0 in a node. And this time we're going to say the algebraic sum of voltages around the loop must sum up to 0. Let me actually put the definition in here in case of any need. Mathematically, actually, we can express this statement. What we're going to have is a summation sign. Here we have m, and m is going to start from 1. And this is basically, this m right in here is representing the loops we have. And then what we're going to say is Vm is going to be equal to 0. That means the voltages around the loop must sum up to 0. And in here we have an example. For instance, let's take that one. And again, we have a convention. In the previous one, remember when we are talking about KCL, I told you that the entering currents must be taken as negative and the leaving currents must be taken as positive. And this time we have the issue of polarity, so you need to be careful about that. What is that supposed to mean? For instance, in this particular loop, we have a current, right? And that current right now is in the clockwise direction. Check out, it is in the clockwise direction. And in here, the convention is this. You either take the clockwise direction or counterclockwise direction. It doesn't matter. The two options will yield exactly the same result. Let's try. So let's try for clockwise first. Just like in this example. So since we're talking about clockwise direction, when we follow the path, this is the direction, right? Here we enter the element V1 from the negative terminal, so this is going to be minus V1, and as we follow the path for V2, the current enters from the positive terminal, so that's going to be positive V2. As we follow, the current enters this element, this resistor, from the positive terminal, so we're going to have positive V3. As we follow the path here, this current enters the element from the negative terminal, so that's going to be minus V4. As we again follow the path, the current enters the element 5 from the positive terminal, so that's going to be positive V5, so that's going to all sum up to 0. And when we do a little bit of an arrangement here, we have minus V1 minus V4. Let's take those to the other side of the equation. V1 plus V4 must be equal to V2 plus V3 plus V5, and this is the result we have. But let's also try it for counterclockwise direction. In that manner, let me get a white pen and delete this current we have, and let's assign a current in the counterclockwise direction. Let me take red, and this time the current we're gonna have will be in this direction. So when that's the case, let me delete the previous operations. Again, take my pen. Here, this time we have a different direction. And let's follow that direction. This is the direction. This time, we are entering the element 4 from the positive terminal, so that's going to be positive, plus we are entering element 3 from the negative terminal, so that's going to be negative, not plus. Let me delete that. This time, we're going to have minus V3. As we follow the path, we enter element 2 from the negative terminal, so that's going to be minus V2. And then, as we follow the path, we enter the element 1 from the positive terminal, so that's going to be positive V1. And finally, we enter element 5 from the negative terminal. That's the reason why we're going to have it as minus V5, and that's going to sum up to 0. And here we have minus V2, 3, minus V2, and minus V5. Let's take those to the other side of the equation. V1 plus V4 must be equal to V2 plus V3 plus V5. And as you can see, these two equations are equivalent. So it doesn't matter which side you prefer to go on. All that matters is to provide stability, provide some trustable foundation on the passive sign convention right in here. It doesn't matter if you choose clockwise or counterclockwise, you're going to end up with having the same thing. And by the way, also here, these two equations, they are equal to each other. They are equivalent, but they are leading us to another conclusion, which is an alternative way to define KVL, which is the sum of the voltage drop, or in a way, let me just put it this way, the voltage drop must be equal to the voltage raise. And this is an alternative way to define KVL, which is Kirchhoff's voltage law. And as you remember in the previous part when we were talking about KCL, we said that there is an application of KCL. And in a similar way, we also have an application for KVL. When voltage sources are connected in series, just like the figure on the left, KVL can be applied to obtain the total voltage. And the combined voltage will be the algebraic sum of the voltages of the individual sources. So what is that supposed to mean? When we actually move on, we can clearly see that. When we go on in this direction, which is going to be, by the way, counterclockwise direction, In that case, what we're going to have is plus V3 because we are entering from the positive terminal. As we move on, we are entering from the negative terminal, minus V2. As we move on, we are entering from the negative terminal again, minus V2 must be 0. V1 must be 0. So we can clearly say V1 plus V2 minus V3 is going to be the way that we define the current, and that's the logic. I mean, why? Because it is clear that this part is having a greater potential, and we know that current flows from higher potential to lower potential. We also talked about this. So current must be in this direction. So by knowing that fact, we can simply say that if you take the passive sign convention as in this way, because please check out the red arrow in here is the way that I define the current, but according to current flows from higher potential to lower potential rule, I can clearly see that my definition of current direction and the opposed way, I mean the supposed way, are different. That's why actually I negate the whole thing. But if you just be aware of that fact, if you just be aware of that current is going to be flowing from higher potential to lower potential, you can simply say that let me just take the clockwise direction, so that what you're going to have is V1 plus V2 minus V3 must be 0. So the combined voltage value to one voltage source will be in this way, and this is how we do it. So this is the end of the lecture. I think you understand KCL and KVL now pretty good. In the next lectures, we're going to solve lots of problems, lots of examples about them, so that you can understand it better, because they are the foundation of lots of circuit methods, circuit analysis methods. So it is really important to know KCL and KVL in a really broad sense. So we will solve some examples. If they do not help, please get in touch with me. Maybe we could arrange a one-to-one meeting, one-to-one lecture, so that I can help you out with KCL and KVL. If you have any questions, please do not hesitate to ask. I hope you will have a very, very nice day. See you in the next video. Thank you for watching.